Alright, so assuming my screen is also visible to all of you, so welcome to the third live session for Introduction to Wireless and Cellular Communications. So, okay, people are now joining. Good. Hey, can you please mute yourself? Kiran,
Back class video and just now.
Kiran, can you just mute your microphone?
Yes, sir.
Yeah. Just noise was coming. That's why I just told you, requested you to just keep your microphone off for the moment. Okay, good. Thanks. So, yeah.
Okay.
All right. So, welcome to the third week of problem solving session on this Introduction to Wireless and Cellular Communications course. And as you know, I am Avik. I am a PhD scholar at the Department of Electrical Engineering at IIT Madras. So I'd also like to wish all of you a happy Independence Day. And so the agenda for today is to discuss some problems related to the contents of the third week. So if you recall the lectures, in week 3 we basically continued with the cellular design aspects and cellular geometry, and then we also studied a few concepts such as handoff and mobility management and outage probability. So we'll discuss mostly numericals related to those concepts, and so let's begin. Okay, I hope question number 1 and 2 is visible on the screen. Let's start with the first one. um, just read the question and feel free to answer if you are already familiar with it. Okay, so we had discussed similar questions last week as well, so should not be a big problem. Okay. Okay, so we are looking at question number 1. Which of the following is not a valid cluster size assuming hexagonal cells? So what do you think? Which of the following is not a valid cluster size out of the 4 given options? And it is mentioned that we are using hexagonal geometry, so hexagonal cells are deployed. So you can just unmute and answer, or you can also write in the chat box, but I prefer if you unmute and answer. So we are looking at,
Is it 11?
exactly, yeah, thanks. So it is indeed 11. I don't know who answered, I think Nandini. So yeah, exactly. So the reason being, a valid cluster size means the number of cells in a cluster. So a valid cluster size n should satisfy this relation. It should be of the form of I squared plus j squared plus I times j, where I, j are integers. Okay, so looking at the options, out of the 4 options, it is option B 11 clearly which does not satisfy this condition. 11 can't be expressed as this form. So there is no, there is no such I and j pair that satisfies this condition for 11. So of course it is not a valid cluster size. 11 is not a valid cluster size. And if you look at the other options, for n equals to 7, if you put I equals to 1 and j equals to 2, that would satisfy this relation, because 1 square plus 2 square plus 1 times 2 gives you 7. Similarly, for n equals to 7, n equals to 27, which was another option, I3 and J3 is a possibility, and for n equals to 19, again I equals to 2 and j equals to 3 satisfies. So out of the 4 options, 11 does not satisfy. So n equals to 11 doesn't satisfy the condition. So your answer is option B, which is 11. So good that you guessed correctly. It's straightforward only. Now let's move to the second question. Okay, read the second question. I'll give you some time to read. So again, hexagonal geometry, n cell reuse pattern means cluster size is n. Base stations at the center of each cell are present with omnidirectional antennas. What would be the D by R ratio? What do we call D by R? It's the co-channel reuse ratio, also denoted by capital Q. So what is the D by R ratio required if a minimum value of C by I equals to 15 dB? So C by I, if you remember, it's the signal to interference ratio. So minimum signal to interference ratio of 15 dB is required, and assuming path loss exponent small n equals to 3, and consider only the tier 1 interference. So in that case, what would be the D by R ratio that would satisfy this condition? Okay. Okay. So hopefully question is clear to you, and these concepts were discussed in the lectures also, and here we'll be assuming the simplified case, meaning that okay, there is a central cell, and central cell, hexagonal cell, and it is surrounded by 6 tier 1 interferers, and we will assume that for the sake of simplicity that they are equidistant from the central cell. Okay, let their distances be capital D. In general, if you recall the exact diagram that was taught in the lectures, some of the cells are a bit further, some of the cells are a bit closer. Let's say D plus R by 2, D minus R by 2, D, and so on. But we'll assume that okay, D is sufficiently larger as compared to R. That's why all the cells can be, all the tier 1 interferers can be thought of to be equidistant from the central mobile station. Okay, so going by that assumption, so if you remember, there was a formula for C by I, the signal to interference ratio. So I'll jump to that. Okay, so yeah, basically this the exact formula, which is, so what is C by I? C by I is your signal to interference ratio. Okay, and it is exactly given by this formula, I running from 1 to I naught di to the power minus n. Okay, this was taught in your lecture notes. So here what do these parameters imply? So I naught here is the number of your tier 1 interferers. Okay, and di, so basically how many there will be I naught such tier 1 interferers. So like d1, d2, d3, so on up to di naught would be the corresponding distances from the central mobile station. So this is di is the distance between the mobile station and the ith interferer, you can say, or base station. Okay, and small n is your path loss exponent. Okay, and r is basically your radius of the hexagonal cell. Okay, which is also equal to your, I mean, distance to any of the vertex from the central, right? So okay, someone wants to join. All right, so these are the parameters present in this expression. This is known to us. So signal by interference. Okay, now for the sake of simplicity, we will be using approximation to simplify things. We will be assuming that all these di's are equal, let's say equal to some d. All the tier 1 interferers are equidistant from the central mobile station. So, and this is actually valid for large cluster size. If your cluster size is reasonably large, then this approximation is valid, as it was discussed in the lectures. So let's look at the simplified expression. So what we are assuming here is these di's are assumed to be the same. My handwriting is very bad, so please let me know if it is not at all understandable. So let's say this di is equal to d basically for all the I. Okay, and what are the given conditions here? If you go back to the question, 15 dB minimum is required, C by I. Path loss exponent n equals to 3 is given. Now how many tier 1 interferers will be present? 6, right? I mean, surrounding the central mobile station there will be 6. I naught would be 6. That was similar diagram, if you remember, was drawn. So I naught here is 6. C by I, the minimum signal to interference ratio required in the problem is 15 dB, and 15 dB, let's convert it to linear scale. So by now you should be familiar with conversions from dB to linear scale and vice versa. So this in linear scale translates to 31.6 approximately. Path loss exponent is given to be 3. Okay, we need to find this d by r. This is what we need to find. That's the setup. Now, so yeah, okay, so now approximate, once you go with this approximation that okay, you are assuming equidistance, right? Then your c by I will, what will it become? Basically you have to replace all this di by d, so it will become, the numerator will remain same, r to the power minus n divided by d to the power minus n, and how many of such terms are there? I naught such terms are there, which is 6 terms. So I naught times d to the power minus n. Okay, so which you can also write it like this, right? I naught is 6 and times d by r to the power n. Fine. So this is your approximate formula. And now if you change the side, okay, your d by r you can write it as 6 times c by I whole to the power 1 by n, correct? And we have computed and make sure here when we are doing this arithmetic, it has to be done in the linear scale, right? We are not taking log here. It's a dimensionless quantity on both sides. We are in the linear scale, so use this value 31.6. that's why we converted from dB to linear scale. So it is 6 times 31.623 whole to the power 1 by n, which is 1 by 3 because small n path loss exponent is given to be 3. Now this will be approximately 738, this cube root, which is approximately 5.74. okay, this is approximately 5.74 d by r. Option C. So your answer is option C. Simple. Okay, so this is the situation of tier 1 interferers. 6 of them are there. We assume they are equidistant, and this approximation holds whenever the cluster size is large, as I say. So now if you go here, if you like, let's say this is aside, okay, this is aside. Now we obtain that d by r equals to 5.74, and d by r we also know that it is square root of 3n. Now this will give you n to be something like some 10.08, but that's not a valid cluster size. So the next immediate valid cluster size turns out to be 12, which satisfies that I square plus j square plus ij condition. So this is large, right? N equals to 12. This is large cluster size. So in this case, this approximation will make sense, will not create a huge difference between the most accurate value and the approximated value. That's right. So approximation can be taken here, and we saw that okay, if we choose that they are equally farther from the mobile station at a distance d, then formula boils down to this, and then we just plugged in the values and obtained this d by r equals to 5.74. Fine, easy enough. Okay,
Sir, I have a question.
yes, go ahead.
This question is asked in assignment. Consider a cellular system with hexagonal cells and cluster size of 3. if 120 degree sectorization is employed in a system,
Hmm.
how many tier 1 interferers will be present in worst case scenario?
Yes.
Now here we have to calculate I0 only, na?
What do you mean I zero? Okay, I zero.
I0,
Yeah, again, yeah. I mean, in this case, there were 6 of them, but now you are employing this sectorization. So of course, it is
yeah.
expected to be reduced. It will no longer
Huh.
be 6. So if you just go through your lectures, you can either do a 120 degree, you can either do a 60 degree. Then what will happen? Okay.
Huh, 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 huh.
Okay. Good.
Okay, so if 120 degree sectorization is employed, then what will happen?
Yeah. So then obviously then you're, I mean, of course, yeah, because 120 means you will be, let's say, I mean, this is, let's say, center of one of the cell. So the emission would be like this would be radiated like this.
Huh, 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 huh.
So effectively, if this is the central one, and let's say surrounding this there are like 1 2 3 4 5 6, let's say I'm just drawing, let's say 6 of them are there. So if they are also emitting like this, this one is the, let's say, the central one. So these ones won't have any contribution to the central base station, right? Because they are radiating in this direction. So
Huh, 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 huh.
so you will count
So
them
they
out.
will not create interference for this one.
Exactly. So
Huh, huh, huh,
this
huh,
way you
huh.
have to take care of this situation using sectorization. That's why, I mean, that's why sectorization is a technique to actually increase your signal to interference ratio by minimizing the interference.
Reduce interference.
Exactly, by reducing interference you are increasing the C by I, which is signal to
Yes,
interference ratio.
yes.
So yeah, of course. So yeah, just I mean, these things are discussed in detail in the lecture, so go through it and should
Okay,
be fine.
okay,
Okay.
okay, sir. Okay, thank
All
you.
right. Okay, so now going to the third question. Third question is also a slightly modified version of the second one. So again, the similar situation is there. In cell reuse hexagonal geometry, and with base stations are present at the center of all the cells, and again, minimum C by I required is 15 dB, and path loss exponent in this time it's 2.5, assuming only tier 1 interferers are present. What would be the value of cluster size? Here you are asked to find the value of capital N, the cluster size. Okay, so in the previous question you were asked about the co-channel reuse ratio, basically the D by R, and which is again root 3n. So now all you need to do is find n. So simple enough again. So you are asked to find this cluster size given the C by I minimum that is needed is 15 dB, which again in your linear scale would be 31.623. Now I am still writing, if someone is confused how do we get 31.63, basically 10 log of x, this is 15 dB. So what is x? X is 10 to the power 1.5, which is 31.623. Okay, this is how you go from dB to linear scale. All right. Okay, wait.
Sir, how we have got this 31.623?
I just wrote it, right? So just look at it. This red ink.
Okay. 10 raised to the power 1.5.
So this is the condition. See, I mean, whenever you go from x is in the linear scale, okay. So when we want to go from linear to dB, we take 10 log base 10 of that value. So
Yes.
that in dB is 15 dB, which is given. This condition we know. Now we need to find x. So how do we find x? That's simple mathematics, right?
Yes,
So x equals to 10 raised to the power 1.
anti-log of, yeah. We will have to calculate anti-log, no?
Anti-log, I mean log, log base 10. So this, from this you get
15. So that means
this,
x
right?
would be anti-log of 15. Anti-log of 1.5, na?
Yeah, I mean once you have log base 10 of x equals to 1.5, so
Yeah,
x, how do you get? X is simply 10 raised to the power 1.5.
1.5. So that is anti-log. That
Yeah,
is anti-log.
I mean, yeah,
Yeah,
I mean, you don't need any anti-log table or anything here. You just need a calculator. That's it.
yeah, yeah,
Just use your calculator. Write 10 raised to the power 1.5. That will give you this
yeah, yeah.
31.62. Okay. So
Yes,
yeah.
sir. Thank you.
Okay. So good. So all right. So yeah. Okay. Yeah, we are in the third question, and this time the path loss exponent is given to be 2.5, and again tier 1 interferers are present. So I naught is 6, I naught is 6, and yeah, again, I mean, we are assuming that all the interferers are equidistant from the mobile station. Okay, so use the approximate formula just as we did before. This, fine. So this is 1 by 6 d by r to the power n, and what is d by r? D by r is square root 3n. For hexagonal geometry, you know this relation. So now you can write it as, okay, root 3n. What will root 3n become? 6 times c by I whole to the power 1 by n. So 3n would become 6 times c by I to the power 2 by n. We are taking just square on both sides. Finally, this will give you n equals to 1/3 6 times c by I whole to the power 2 by n. Now just substitute the value. 6 times your c by I is 15 dB, which is 31.623 in linear scale, raised to the power of 2 by small n. Small n was the path loss exponent, which is given to be 2.5. And this, if you just calculate, approximately this is turns out to be 22.15. Okay, so since the c by I minimum required is 31.623, this cluster size minimum required should be this value, right? And okay, and now one more thing. So now you may be tempted to think like, okay, that means, okay, n is at least greater than 22.15, so n should be minimum 23. Fine, I am done. But no, that's wrong. Why this is wrong? Can you tell me what should be the value of n? Anyone? So at
25.
sorry,
25, sir.
25. Yeah, I mean 25. So like I equals to 5, j equals to 0. That would give you basically I square plus j square plus I times j which is your 25. So yeah, n equals to 25 is, I mean, the thing is typically it is not used. I mean, although algebraically it satisfies, but typically this 25 is not used. So what we do is we rather go for n equals to 27. So for I equals to 3, j equals to 3, that satisfies 3 square plus 3 square, yeah, it satisfies. So yeah, we rather go for this value, n equals to 27. So that's the next immediate, actually. This is the next highest integer that tessellates. So see, if you look at the options, 27. So 25 is typically not used, actually. So the next immediate would be 27. But good, I mean, 27 clearly also satisfies this condition. So answer would be, I think, number what? Okay, option C. So option C, 27, would be the right answer. Okay, just a second, someone wants to join. Okay, wait. Okay, good. So yeah, all right. So question number 3 is done. Now question number 4 is also very similar. I think it's again you have to find the optimal value of n, and everything is given. Minimum C by I required is 9 dB, and path loss exponent small n is 3. Again, assume tier 1 interference. So it's again the same, and it is already mentioned here that, okay, by the way, for this question also, you see, this is also, very large cluster size, right? So since this is a large cluster size, our approximation is fine. We are good with the approximation. It won't make a huge difference. So, and question 4 is also exactly similar to question 3, with just the, I think, data are different, and we need to use the same thing only. So it should be easy, but still I'm just writing, okay, the final value. So this is like just the value is different here, 9 dB. So again, this is 7.94 in linear scale. Same setup is there, okay, same setting as question 3, and small n here is 3, I naught again 6. So just use this formula, okay, which is 3. Okay, so and yeah, so this will give you n equals some 4.38. So n has to be larger than 4.38 at least. So again, the next immediate value would be that satisfies this would be this, n equals to 7, and n equals to 7, you can think like I equals to 2 or I equals to 1, j equals to 2, whatever. I mean, the order doesn't matter. So this will give you n equals to I square plus j square plus ij. So this is the next I mean this should write it like this actually. So next highest integer that selects. Okay, so n is 7, and so option A answer is option A, same as question number 3. Now going to question number 5. Yeah, read question number 5. I'll give you some time. This is an easy one. You can just unmute and say the answer. It should not take you long. Question number 5. Okay, so there is a cellular system with 10 users, and each user makes an average of 2 calls in 1 hour, 2 calls per hour, and each call on an average lasts for 6 minutes. So that's the average call duration of the holding time, if you remember. And we are asked to find what is the total offered traffic, and the unit is Erlang, as you know. So it's again, I mean, simple, just the formula that you have to use. So alright, so number of users, we typically denote this by U, remember, in the lecture. So that is given to be 10, and the call arrival rate, basically call arrival rate, which is your average number of calls per hour and per user, is, and we typically use lambda to denote this. This is 2 calls per hour. Okay, this is given. Another thing which is given is your average duration of call, every call, which is also known as the holding time, right? Holding time, H, denoted by capital H, is 6 minutes. And since we want to keep the units uniform, so they should be matching. So since we already used calls per hour, so here we will convert from minutes to hours, so which is 6 by 60 hours. Okay, let me admit. Okay, so we have this information, and now we need to find the total offered traffic, and of course the unit is Erlang. This is how much. So okay, I think someone answer will be 1 Erlang. Okay, let's see. Okay, so firstly, traffic, you need to find the total offered traffic. Fine. So firstly, traffic per user you have to consider. For one user, what is the offered traffic? That is typically denoted by A suffix u, which is simply your lambda times h, right? The calls per hour times your holding time, average duration of call. So what I mean is your I mean so this is like 2 calls per hour times 6 by 60. We just calculated this. So this
answer will be 2 all along, most probably.
yes, correct. So this can be simplified to be, I think, 1 by 5. So that's your traffic per user for one user, because we just wrote the data for one user. One user gets call, 2 calls every hour, and each call per user lasts for 6 minutes on an average. So this is traffic per user. Now for finding your total traffic, you need to just multiply this traffic per user with the total number of users. That's it. So number of users times traffic per user, right? So this is total number of users is how much? 10. It is given 10 times 1 by 5, which is the traffic per user we just calculated. So this is 2 ln. Okay, so 2 ln is the total offered traffic, and going to the options, it is option D. Option D is your answer. So okay, let me check there. Yes, yeah, correct. Okay, fine. Okay, question number 5 was straightforward. Now there's another question on this traffic capacity. So question number 6, okay, here you are asked to find the blocking probability. What is the probability that your call is blocked? Remember that P blocking, probability of blocking. Given that the system has 50 channels, number of channels are given 50, and the maximum capacity per channel, so this is the traffic per channel, that is 0.758 airlines. Okay, and there's a very useful tool which the link I have given here. It's actually an online airline B calculator. Basically, you can just enter some of the values, and whichever parameter you need to find, you can basically find it just by entering. So I'll give you a demo of this. So okay, so let me first write it down basically. Okay, so we are in question number 6. We need to find this probability of blocking, given that, okay, number of channels is 50 given, and the capacity per channel, let me look at it once again, yeah, is 0.758. so this is 0.758 lengths. So therefore your total capacity or the total traffic would be the capacity per channel into number of channels, which would give you 0.758 into 50, which is 37.9. This is Okay, so now, so you have, hello, yes, is there a question? I think someone is I think someone's mic is on. Maybe if you have any questions, you can ask, or you can just mute yourself, please. Pedia Thambi, can you please mute yourself?
Sorry. Yes, sir. Sorry.
Yeah, no problem. Just mute. Yeah, thanks. All right. So yeah, so this is the thing. Okay, so we have the traffic. So this is your traffic in airlines, and this is your number of channels. These two data you have. Now you need to find this probability of blocking. This you have to find. So let me just give you a, so this link actually take some time. So yeah, this is an online LNP calculator. So see, there are three columns that you can control. So here we know we need to find the blocking probability. So the first one is the airlines, the traffic. The second column is blocking, which means the probability of blocking, and the third one is lines, which means your channels. Okay, so airlines, we just calculated that it is equal to your 37.9, right? So 37.9. So you can, so first you need to choose actually out of the three, which one do you want to calculate. So I'll just check this blocking because we want to find the probability of blocking. Now I will manually enter the value of airlines, which is 37.9, and the number of lines or number of channels is given to be 50, and just click this calculate. So you see the blocking probability, it shows 0.01, which is 1%. So using our LNP calculator, we found that probability of blocking is 0.01, which is basically 1%. So look at the options. Option B, 0.01. So option B, 0.01. Now if you remember in the lectures, Professor David had shown you a graph which was given in the textbook of Rappaport. So I could have shown you that as well. Let me just a second. So it's basically the same thing only. Graphically also you can visualize it. So I think it's some page number 49. I don't know, it's the same. So this is the wireless communications book. So maybe I can just search by this keyword. Let's see if we can find this Okay. Okay, this graph was, yeah, this one, right? I think mostly this one, yeah. So this graph, so I think in page 49 of Rappaport. So you see on the y-axis we have probability of blocking. On the x-axis we have the traffic intensity in airlines, and all these different plots are for different number of trunk channels, number of channels basically. So this, the leftmost one here on the top corner, is for number of channels equal to 1. This one is for number of channels equals to 2. This is for number of channels equals to 3, and so on. It increases from left to right. So given our problem, so we saw that, okay, number of channels is somewhat 50, so which is like this line. I hope I would have been able to zoom it, but this line, this 50 line, this one, which runs like this. So number of channels, if you choose to be 50 in this graph, and if you choose the airlines traffic that we calculated came out to be 37.9. So and note that this x scale is actually in the log scale, so they are not, so after this 10, basically this point is like 20, this is 30, this is 40, this is 50, 60, 70, 80, like this. So the traffic is very close to 40, something like 37.9. so it is somewhere like, this is 20, 30, 40, like here, somewhere here. So if I travel up from here and go till I reach this 50, till I intersect this 50 line, number of channels equals to 59, somewhere I will land up somewhere here. And if you see the corresponding y scale, I mean the value on the y scale, the probability, which is close to 0.01. I mean, you can visualize it fully. So both are the same thing. So you can do it online also using this tool, or if you have this graph, this chart, you can just use some scale and mark out the points that you need. So that's the thing. So anyways, so that was fine, the question number 6. And now let's go to question number 7. Question number 7 is a conceptual question, so read it.
Sir, excuse me.
Yeah.
Sir,
Yes, tell me.
sir, the question is asked in assignment. In a normalized UV coordinate system,
Yes.
consider 2 points
Yes.
with the following coordinates: point A 3 minus 3 and point B minus 3.
Yes.
What is the actual distance between points A and B
Yes.
if the length of each side of hexagon is 1.2 kilometer?
Yes. I'll come to that distance calculation problem later. I'll come to
Okay,
that.
okay.
I'll come to that. So now let's
Okay.
go one by one in this sequence.
Yeah,
I'll
yeah,
come
yeah.
to
No
that.
issue, sir.
Yeah.
Yeah, yeah. I have 2 more problems about which I have doubt. Means to clear the concept, I
Oh,
have to ask
okay. If
2 more
time
problems.
permits, we can do it, or else you can drop me an email or just post it in the discussion forum. Whatever doubts or queries you have.
Okay, sir. Means we have to submit assignment by tomorrow, na? So
I'm not sure about the deadline. I think, yeah, maybe
yeah,
16th.
yeah,
Yeah.
16.
Okay.
So I have to clear those 2 doubts. Means 2 problems more.
Okay, so let's look
Yeah,
at
yeah.
this.
Okay,
So
okay,
question
sir.
number 7. It's basically two statements are given. You have to find out whether they are true or false, like that. So what happens, which of the following statements is true if you increase the number of cells in the cluster? So basically, if you increase the cluster size, the number of cells in cluster, it says, statement 1 says that the C by I, the signal to interference ratio, reduces. Option 2 says that the airline capacity increases. Now there are 4 options that, okay, only one, statement 1 is true, only statement 2 is true, both are true, neither of them are true. So you can answer if you, I mean, these observations were clearly, noted on the class, in the live, I mean, in the videos, if you have seen, or the lecture notes. So okay, let me, maybe I'll go to the next page. So 7, if you see, so basically what they are saying is they are increasing the number of cells in the cluster, so they are increasing that capital N. Now statement 1 says that then in that case, on increasing number of cells, the C by I drops, reduces. Is that true? So I clearly know that it's not, because it will grow proportionally. Why proportionally? Because you know what is your C by I. C by I is, remember that approximate formula. Okay, wait, this is 1 by I naught times d by r to the power n. So this is equal to, and d by r, how can you write d by r? That is square root of 3n, right? So this is 1 by I naught square root of 3n to the power small n. Now hopefully these parameters are known to you. I naught is the number of tier 1 interferers, capital N is the cluster size, which is actually our input in this case, and small n is the path loss exponent, and the square root of 3n is a quantity which is greater than 1, right? So it will grow as we increase it. And so clearly, as from this expression, as n increases, your C by I also increases, isn't it? So clearly your statement 1 is not true. So statement 1 is not true. So your statement 1 is actually false. This is false. Okay. And now coming to the second part. In the second part, it is given that the airline capacity increases. Okay, let's look at that as well. So basically what happens is that you are increasing the number of cells, okay, cluster size, you are increasing the value of n, number of cells in cluster, whereas you are not changing the number of channels. So the number of channels per cell will effectively drop down, and that's basically your capacity, right? So that will reduce. So it is mentioned that capacity increases, but it actually reduces effectively. What I mean to say is that if, let's say, okay, this like this, let's say you have, I mean, it's not drawn to scale. Let's say you have this initially, let's say cluster size of 3, fine, 3 cells, and let's say you had total number of channels equals to let's say 30, and if you divide them equally, then let's say in each cell you can allot 10 channels each, total 30. Now I am growing from here, I am now increasing n, I am increasing the number of cells, let's say from 3 to 4. So if I have for cluster size 4, I am having something like this. I mean, this is not at all it's a very bad diagram, but just for illustration. Okay, so let's approximately assume it to be n equals to 4. These are actual regular hexagons, okay, they are not drawn to scale. Again, number of channels remains the same, you are not modifying that. Now if we want to evenly distribute the number of channels to all the cells, what will be the number of channels per cell? It will be, so number of channels per cell would be 30 by 4, right? Initially it was 30 by 3, which is 10, but here it will be 7.5, so which is less than 10. So now your channels per cell decreases, as a result of which your L-line capacity will also reduce, right? And so statement 2 is also false. So the argument is that as the number of channels remains same, when the number of cells, basically the cluster size, increases, the number of channels per cell decreases, right? So number of channels per cell decreases, fine. Now if you go to this diagram here, okay, from right to left you see all of these lines. From right to left, if you go, the number of channels are reducing, right? So for a fixed probability of blocking, let's say you fix this y-axis, so if you travel from right to left, you look at the x-axis, what happens to your traffic intensity in airlines? That is also reduced, right, from right to left. So that's what the intuition here is. So if you assume, now assuming the blocking probability is kept constant, the Erlang capacity decreases as number of channels per cell decreases. Okay, that graph I just showed you, right? This kind of a graph. So this was traffic in lengths. So and we had graphs like this and these kind of lines, and they get more crowded eventually. So your, let's say this is this is c equals to 1, this is 2, 3, so on, like this. So these are your trunked channels, and this is your p blocking. So for a fixed blocking rate, for a fixed blocking probability, if you move from basically your right to left, then your Erlang capacity will reduce, right? As your number of channels per cell also reduces. So that's the intuition, as channels per cell reduces. Okay, so this is for fixed P blocking. Okay, fine. Now, so this was a conceptual question. Yeah, question number 7. Now look at question number 8. Question number 8 also, it has been discussed in the lectures, log normal shadowing. Okay, mobile phone receiver operates in a bandwidth of 2 megahertz. Bandwidth is given, temperature is given 300 Kelvin, noise figure is given 4 dB, receiver is present on the cell edge, and minimum 3 dB SNR is required for reliable communication. Consider log normal shadowing effects with sigma equals to 6 dB. You remember that sigma parameter, it was like the Gaussian random variable x that you considered, which has 0 mean and standard deviation sigma, basically that's the thing. And carrier frequency is 2 gigahertz, and to achieve 90% probability coverage, find the mean received power, that PR of D bar, that mean received power. So and given data is there, the Q function evaluated at 1.2816 is equal to 0.1. If you recall the lecture notes, the probability of outage we found, right, that was given in the form of this Q function, Q of beta by sigma, where beta is your shadowing margin and sigma is the sigma which is given here. So that was the probability of outage. So here 90% coverage probability means 0.9 coverage, which means the remaining is the outage. So 1 minus 0.9 is 0.1 is the probability of outage. So that is given, and exactly that Q function value is also given here. See, so this Q of 1.28 whatever is there, this is basically your Q of beta by sigma, that thing, if you compare the two forms. So sigma is already given here, you can find beta. So now you know the shadowing margin, and then you can just find that mean received power, PR bar of D, which basically which is your minimum received sensitivity power, that P mean, or the receiver sensitivity, plus added to your beta, which is your shadowing margin. So I mean I said a lot of stuff, maybe it's difficult for you to understand it, but I mean we have solved, I mean Professor David had solved this kind of things, or at least he has worked out the derivation. So I hope you'll be able to relate with that, the parameters. So I'll go here, do it step by step. Wait. So question number 8. Question number 8. First I'll write the given information. Bandwidth is given. It's 2 megahertz. So it is 2 power 6 hertz, 10 to the power 6 hertz. Temperature T is 300 Kelvin. Noise figure is given, and since it is in dB, so it's essentially that 10 log base 10 f, that thing, that is 4 dB given, and the f here is the linear parameter, which is in the linear scale, and we often call it the noise factor. So the noise factor in dB is the noise figure. So anyways, now SNR, basically the minimum SNR required for reliable communication, this was 3 dB. Okay, someone wants to join. Okay, yeah, minimum SNR required is this. Okay, great. So this is the given information, and also like the carrier frequency was given, but we don't need it at this stage. So okay, fine. So this sigma, this log normal shadowing is mentioned, as a result of which you have this sigma parameter, which is 6 dB. So remember you had the lecture notes. So like x suffix sigma was x suffix sigma, this was a random variable, basically Gaussian mean 0, random variable with I think standard deviation equals sigma. Okay, basically the PDF form which it takes, right? E to the power minus x minus mu by twice sigma square, this, right? This Gaussian PDF, Gaussian PDF. Mean 0 means this mu will be 0. So anyways, so this is the sigma. Sigma is also given, and I'll go to the next page because we run out of space. Okay, coverage probability is given to be 90%, which is 0.9. so which means your probability of outage is 0.1. okay, and you recall that probability of outage, so recall lecture notes. Your probability of outage is given by Q function of beta by sigma. Now where beta is your shadowing margin, and beta is given by this difference basically. Okay, so what are these? So where beta equals to your shadowing margin, so clearly it's a difference of these two, right? So it's a margin, shadowing margin, and PRD, this bar denotes the mean. So this is the mean received power. This is the one we need to calculate in this problem. And P mean means the minimum transmit power that you need for reliable communication and reception of the signal. So that's the minimum, that's the signal, received signal sensitivity basically. That's the minimum that you need. So this is actually your received signal sensitivity. Okay, fine. And sigma I had already mentioned. So now it is given, one data is given in the question, that Q of 1.2816 is equal to 0.1. Now 0.1, we just found that 0.1 is same as your outage, right? Probability of outage. So this is your same as probability of outage, and which is given by, I just wrote here, beta by sigma, Q of beta by sigma. So what do we have? Beta by sigma equals to 1.2816. So beta is 1.2816 times sigma, and your sigma was given to be, I think, how much was it? 6, I think. Yeah, sigma was 6. Yeah. So this times 6 will give you beta. You will get beta as approximately 7.69 dB. Okay, this is a shadowing margin. You found your shadowing margin. Okay. So, and that is also equal to this mean received power PR of D bar minus P mean. This you know, this difference you know, this margin you know, and you need to find. Yes.
Sir, 6 dB is in dB scale. No, we have to convert into linear scale now.
No, in this case dB scale only you have to stay, because this is the margin, shadowing margin, the difference, that the difference, I mean, is the ratio of power, but it's the difference between the mean received power and the received signals sensitivity. So here note that it is in dB. So, and of course q of something, the parameter inside should be dimensionless. So sigma is also in dB, beta is also in dB, that's why. Okay, so in this case you have to stay in dB. Yes, this is important. So here you have to be in dB, because then only sigma and beta, the ratio would cancel out, it would be dimensionless, right? So okay, this is fine. 7.69. So now we need one more thing, which is this P mean, which is the received signal sensitivity. If you find that and you know beta, the margin you know, then you can find this mean received power, right? So let's find P mean. And what is your P mean? P mean is your received signal sensitivity that I just mentioned. That is equal to, and that same old formula we know, that 10 log base 10 KTBF plus your SNR, and this term actually is called your noise floor, basically the noise component. And in addition to that, the signal to noise, the margin that you need, this is SNR in dB. So that will give you the minimum power with which you have to transmit, so that you are able to receive correctly and decode correctly. That will give you the receiver sensitivity, basically. Fine. So do keep this is very important formula, so keep this, it will be handy every time. And so now I can split this KTBF log into some 3 terms like this: 10 log base 10 KT. First term I can write, second term, okay, 10 log, second term I can write like this, only the B. Third term I can write like this, okay, and we have the SNR. And this, what is K and T? I think these are known to you by now. K is the Boltzmann constant and T is the temperature. So just if you plug in those values, you will get minus 174 dBm. You should be familiar with this by now. So basically all you need to do is put Boltzmann's constant, K equals to 1.38, I think 1.38 into 10 to the power minus 23 joules per Kelvin, and put temperature equals to 300 Kelvin, which is already given in the question. And here this will give you 63 dB hertz, and put B equals to 2 megahertz, which was also given in the question. Okay, and this is already given, the noise figure, which is already given as 4 dB, and the minimum SNR was also given, which is 3 dB. If you add all these components together, then you will get P mean, the minimum power or the receiver sensitivity. This is your received signal sensitivity. This will be minus 104 dBm. Okay, people are joining now. Okay, this is what you will get. Now you have everything, so all the ingredients are ready. Now you know, you already calculated the beta shadowing margin. You already calculated to be 7.69 dB. So therefore your mean received power is simply the sum of these two, right? P mean plus beta, which is how much will you get? This will give you, I think, minus 96.31 dBm. That's your mean received power. If you go back to the options, option B, I can clearly see is the one. So answer is option B. Okay, simple, just formula based. Like you mentioned that, okay, here we have to deal with dB because it's a margin. It is difference between the two powers, therefore it's a margin in dB that you have to be careful about. So, and then you found beta given sigma and the Q relation, and you calculated the P mean, which is the received signal sensitivity, and you just added it to the shadowing margin to find the mean received power. Okay, that which was asked in the question.
Sir, one thing in the calculation. Hello.
Yes.
In the calculation, when you have calculated the P mean,
Yes.
P mean, there are we have seen that 4 terms you have added, but there are one is dBm, one is dB hertz, and other is dB.
Yeah.
But you have given the total, when the sum up, and the total unit is dBm.
Yes, because ultimately what you are getting is a unit of power. Okay, P mean means received signal sensitivity. It's a unit of power, and all these things, the remaining things, they are dimensionless quantity. This is SNR, this noise figure, this bandwidth, these are dimensionless, and these are just the margin. Okay, they will add up as it is, but overall you will get dBm. Just because it's the unit of power, like previously we had done. Okay, let me just, when you do that free space model, you know that PR equals to PT by some path loss, which is 4 pi d by lambda square. This 4 pi d by lambda. Exactly. So this path loss is dimensionless, right? So when you go to the dB scale, so this path loss is given by your PT in dBm minus your PR in dBm. So it's the difference. So ultimately you will have dB. So in other words, you can add this dB to that dBm like this. So basically it's a dimensionless quantity at the end of the day. So that's the thing. So once you convert it to dB, you can just add it. Okay, you need not worry about it.
Okay,
so and also you can I think in lecture notes or in the videos Professor David has mentioned about this. Even if you still find it confusing, you can go through some of the books also, standard books, textbooks. There are many reference books, so I think it should not be a problem. But yeah, so all right, so that's the thing. dBm means dB milliwatts or dB watt. So this is basically your when we talk about dBm, it's like 10 log base 10 of the power in milliwatts divided by 1 milliwatt, that relative to 1 milliwatts, that's the power here. And dB watts means relative to 1 watts, so dBW. So these are units of power, absolute power. And only dB means just a margin, it's a dimensionless quantity. We are not talking about power there. So these are margins, SNR, noise figure, these are margins, these are dimensionless, dB. Okay. Okay, I think we are done with question number 8, and question number 9 is an extension of this problem. So the data is same, I think. We have already considered this scenario, and an additional part in this question says that, okay, given there is maximum power constraint of 1 milliwatt that a base station can transmit. So maximum you can transmit 1 milliwatt. Find the maximum radius of the cell, means the distance, basically the range, for 90% coverage probability. So 90% coverage means 0.1 outage, the same, and that same Q condition is given, and as you have to assume free space path loss model, and carrier frequency is 2 gigahertz. You need to find the range D. So let's try to do it. Okay, so this is continuation of question number 8. Okay, so you need to find the range, the D. So but before that, let's look at what is given. Firstly, you have to assume the free space path loss model. It is mentioned in the question, and the transmit power PT is given to be 1 milliwatt. And how much is 1 milliwatt in dBm? Can someone quickly say in dBm?
30.
Sorry?
Is it? No.
0, sir.
Yes, 0 dBm, because when you measure in dBm basically power in dBm, this m is that m for milliwatts, okay, is equals to 10 log base 10 of your power divided by 1 milliwatts. So I mean, since here your power is 1 milliwatt, so this ratio becomes 1, so log of 1 is 0, that's why it becomes 0, right? So this is how you go from milliwatts to 1 milliwatts maps to 0 dBm, basically. This is how it happens. So this is given. Your carrier frequency FC, let me denote it by FC, is given to be 2 gigahertz. So in free space path loss model, I remember I have this d by lambda, 4 pi d by lambda, so I need lambda. So let me find the lambda from this C by FC, so which gives me 3 by 20, I think, meters, which is 0.15 meters. Okay, now okay, so what's the model? This is our equation. The received power at distance d is transmit power divided by the path loss. Okay, this is the path loss, PL. Okay, so path loss is this. Okay, now path loss, and see, this is in linear scale, this is dimensionless because distance, wavelength, they cancel out, they are same units. Now path loss in dB, and these are ratio of the transmit and receive power, right? Ratio of power, again a dimensionless quantity. Path loss in dB is 10 log of this value, which is 20 log. So this 2 exponent comes out as a multiplicative factor. You have this, and so basically, as I was mentioning few minutes back, this is again your ratio of the transmitter and receive power, right? So, and that will basically be the difference in the dBm. Ratio in linear scale will be like a difference in the log scale. So that is the difference between the absolute values of your transmit power. So this is your transmit power minus the absolute received power. Okay, and so 1 milliwatt is the transmit power, which is 0 dBm, as someone told it correctly. 0 minus, we just calculated this one, the mean received power in the previous part. We just calculated this, right? Mean received power, how much was it? Okay, minus 96.31 dBm. So minus of minus 96.31, this is plus 96.31 dB, because this is path loss. Again, it's a margin, it's a dimensionless quantity, that's for 3B. This is not power. Okay, all right. So so what do we have? So now, okay, and this is what this is. So 20 log base 10 4 pi d by lambda is this, and now you can solve for d. You already have lambda. Put lambda equals to 0.15 meters. Already you have calculated this. I have calculated before here. This place, so we get d equals to nearly approximately 780 meters, which is 0.78 kilometers, and that will be option A. So option A will be the, so that's the range, that's the radius of the cell up to which this will be guaranteed. Okay, if you are sending with 1 milliwatt power, you can cover this much range given all these conditions. So yeah, fine. I think we are running short of time, so okay. And question number 10, again it's a kind of a visualization problem. So question number 10 says, okay, which of the following fact is true about maximum per channel capacity? So the channel capacity per channel for a fixed probability of blocking. So again you have to visualize that graph actually. That y-axis was the probability of blocking, x-axis was the traffic inner lengths, and we had different plots for different number of channels, right? And so for a fixed probability of blocking, how are this uh, capacity per channel and the number of channels, they are related, how they are related. So for this actually you can use this online tool also, which I just showed you before, is the same one only. So what you can do is, wait, I don't know what is happening. Okay, so in order to visualize how it looks, so you can fix they mentioned that you can fix your probability of blocking for a given probability of blocking. So you can choose it to be 0.01 or whatever, and then what you can do is, maybe you can just vary this number of lines or the number of channels. Let's say you increase it eventually from 0, 1, 2, 3 and so on like that, and find the airlines, but that will give you the total traffic, right? So but here in the question it is asked that what is the capacity per channel, so you have to normalize that with the number of channels as well. So basically what I have done is okay, so this is question number 10. Okay, question number 10. So fix P blocking equals to, let's say, 0.01, that I have done, or you can do with any other value as well. So now this is, let's say, my P blocking, this column. Then I have this lines means basically channels, number of channels. Okay, then I have the capacity in airlines, then I have the capacity per channel. Okay, you can form a table, construct a table like this. Okay, we are not having much space here, but anyways, so what I found is, since I kept this constant as 0.01, for one channel this both of them are basically 0 and 0. For 0.01 this will remain same, this probability of blocking is fixed. For two lines you will find these. Okay, 0.15 by 2. I am just dividing the airlines by channels on the last column. So how do you obtain this? You again go to the here. So you need airlines. Let's say I give two lines, two channels, and probability of blocking I have fixed at 0.01. I am finding airlines, the capacity. So I clicked calculate, it showed me 0.15. See, 0.15, that's what I have written here. So, and similarly you can find other values as well, like this and so on. Okay, and so on. So I had found it till some 10 or something like that, number of channels. And you will observe, what you will observe is, so see, initially this capacity per channel, that grows as you increase the number of channels, but what you will observe is, as you keep on increasing, so I leave that as an exercise to you, just plug in the values and see, or from this graph also, from this graph in Rappaport also you can see. what you will observe is that initially, as the number of channels is small, let's say 1, 2, 3 like this, in this regime, the increase in the number of in the capacity per channel is rapidly increasing. They are rapidly increasing in the initial for low number of channels. But as the number of channels increases, approaches let's say 7, 8, 9, 10, then that growth is not that rapid. Okay, so then the capacity per channel increases slowly relatively, and so that is the observation. So what happens is, for a given blocking probability, as the number of channels increases, the traffic intensity or the capacity per channel increases rapidly. Initially increases rapidly in the starting for smaller number of channels, when the number of lines or number of channels is like 1, 2, 3 in that region, for smaller number of channels. But it increases slowly for larger number of channels. And what kind of a graph you will get in such a scenario? So you can imagine actually. So let's say this is your number of channels. I am looking at the traffic per channel or the capacity per channel versus number of channels, because that's what asked in the question. So what you will observe is that, so let's say this is 1, 2, 3, 4, 5, 6, 7, and like this. So and this is some values are there, let's say. So I just showed you 1 or 2 values in this list, but you can form that table, complete that table. I didn't mention all the values because of space constraints, or maybe I can just mention one or two more values. So for number of channels equals to 4, you will get 0.85, which is 0.2125. For 5 you will get 1.35, which is 0.27. For 6 you will get 1.9, which is 0.3166. So clearly you see, and so on. So clearly you see the transition from 0.27 to 0.31, it's the difference is like 0.04 approximately, whereas initially you see the transition from 0.075 to 0.15 is like 0.07. So the increment is more in that region. So as the number of channels increases, the growth is lower, I mean relatively less. So that's what happening here. So I mean you will get a graph like this, and eventually it tends to saturate like this. I mean the growth drops, and we call these kind of functions to be concave down increasing. Since it is increasing, but eventually the increase is, you know, saturating. I mean, as the number of channels is growing, the increment is getting lesser and lesser. So this is concave down. We call this kind of graphs as concave down. So that is a concave downwards function. So option A. So option A is your answer. Okay, this is just an observation, you know, based thing. So yeah, in the usual graph in the textbook, you visualize the probability versus the traffic, but here you're asked to visualize the traffic versus channels. So this is how it looks like. Anyways, so let's quickly move on to the next couple of questions. So all right, so question number 11. Okay, Doppler shift. So there is a base station and there is a user, and the user is moving at a speed of 108 kilometers per hour towards the base station. If the base station is transmitting at I mean it's 2.4 gigahertz, so then what is the maximum Doppler shift? So Doppler shift arises, it's a shift in the frequency basically whenever there is a relative motion between the source and observer. So you can think of it as the source is the base station and the observer is your user, and the user is moving actually. Let's say you are sitting in a car with your mobile phone and that is approaching the base station. So there is relative motion, right? Because the base station is static but you are moving towards the base station. So there is a relative motion between them, and the observed frequency, the frequency of transmission is 2.4 gigahertz, but the observed frequency will be slightly varied. There will be a shift in that frequency due to this relative motion. So that's what we need to find. And so there's a simple, very simple known formula for that. What is that formula? So you have this base station, you can imagine this to be the source, and let's say this is you're in a car like this. Inside that you have your mobile, and that car is approaching, okay, with some velocity. It is approaching the base station. So this is your observer. So the Doppler shift or the Doppler frequency shift let me denote it by some delta F is actually given by delta V by C into F. And what are these parameters? Where your delta V is the relative velocity between source and observer, okay. And F, obviously F is the frequency of the wave, okay. And your C is speed of light wave, because we are transmitting EM waves and they travel at the speed of light, and the medium that we are considering here is air. So there is line of sight, and so speed of light in air basically, because the medium is air since it is line of sight environment. And so yeah, that's it. So what will be your delta V? Basically delta V is basically the velocity of this observer, right, which is V minus velocity of base station is 0, it is static, and which is V. So V is given in the problem as 108 kilometer per hour, and I would prefer going from kilometer per hour to meter per second. So for that I can multiply, there's a shortcut trick to multiply it by 5 by 18 to get meter per second. So this cancels out, so this is 30 meters per second. Okay, and I have the frequency of transmission, which is 2.4 gigahertz already given, which is in hertz would be into 10 to the power 9. Speed of light, you know. Therefore the Doppler shift and Doppler frequency shift delta F is delta V F by C, which is by this, and that is 240 hertz. Okay, 240 hertz would be your answer, and that is option C. Okay, just a simple formula. Okay, this is the formula for Doppler shift. Fine, right? Fair enough. So this is simple.
Sir,
Yes.
excuse me.
Yes.
Sir, so maximum Doppler shift is observed when user is moving towards base station, na?
Yeah, I mean, yeah, because so that's the thing. Or I mean, it is, since it is approaching here, so I am assuming the base station is static. So or rather, if there, I mean, both of them are approaching towards each other, then the relative velocity would be even higher. I mean, so I mean, V observer minus V base station, in that case that difference would be even more, because both of them would be approaching towards each other. So that delta V would be even more. So in that case the spread would be even more, and this is the condition which is okay. Base station is static, source is static, I am the observer is approaching the source. So okay, the relative velocity will be simply V minus 0, which is V.
Yes.
So but
So it will be less, one is at rest.
In this case the base station is at rest, so I just subtracted 0. I mean, it makes no sense. I mean, only it's the observer, the relative motion between the source and observer is only because of the observer, which is moving at a speed of V, which is given as 108 km per hour. So that's your delta V only.
Yeah, and when both are moving, then what will happen?
So let's say if in this case the base station would have also moved towards left in the same direction at a speed of, let's say, 8 km per hour, then your delta V would have been 108 minus 8, which is 100 km per hour. Okay.
So it would have been reduced.
It would have been reduced. Both are moving in the same direction, but if they are moving towards, if they are moving towards each other, that means if the base station is moving opposite to that of the observer, that is they are approaching each other, then it would have added up basically.
Approaching each other, then it will get added.
Exactly, because it's vector, right? So V, let's say this is V1, this is V2. Okay, so if you subtract V1 minus V2, I mean, since this is already in the opposite direction, so effectively we will be adding. That's your delta. Okay, I mean,
minus minus plus it will be.
I mean, what I can say here is, let's say this is V1 equals to, let's say, 8 meter per second, and this is, let's say, V2 equals to it, both of them are approaching, so this is also, let's say, 8 meter per second, but since the direction is opposite, if I consider this to be towards right to be plus, then it will be minus. Now what is delta V? Delta V is the difference, the relative velocity. So this is 8 minus of minus 8, which is 16. So it will, I mean, both the observer and the source, they will look like okay, the observer is also coming towards me and the source is also coming towards me, so effectively the relative velocity will be double of them, right? Because both
Yeah.
are approaching each other equally at an equal speed of 8 meter per second. So effectively that would be your relative speed, which is twice.
That means if base station is there,
Hmm.
and when we are moving towards base station,
Hmm.
then base station is always stable, na?
Yeah, yeah.
So if we are moving towards base station,
Hmm.
then in that case delta V will be maximum.
Yeah, I mean, yeah. I mean, in this case, it doesn't really matter because the other component is always 0 because base station is static, right? So, the ultimately delta V would be the only because of this observer, I mean, the user mobile. So,
Yeah.
so there is not really a big question of relative velocity in this picture because we are assuming a static base station always in general.
Yeah.
So,
So either we are so even if we are moving away from base station, even if we are moving towards base station,
it will be the same. The
uh,
overall magnitude of the shift, the frequency shift, that will be the same.
that will be the same.
Yes,
Yeah.
yes, that's the
But then maximum Doppler shift will be obtained.
that's what the general condition I was talking here. Let's say they both are in motion. That's a more general case. Let's say
Yeah. 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 But in case of base station, which is always a stable,
static.
yeah, static. So in that case, it doesn't matter. No, means
No, no.
maximum Doppler shift will not be obtained in both the cases. If even if we are moving away from it or
It will be the
towards it.
same. The shift will be the same.
Yeah,
Yeah.
but then in that case, there is another formula, na, sir, that cos theta something due to which we will say in direction when it is in direction perpendicular to the line of sight path.
Cos theta. I mean, in this case, we are assuming that they are.
Doppler shift is also having one formula, na, in terms of theta.
I
Is it there?
mean, that would depend if, like, since here in this example, I assume that okay, they are along the same line, but if velocity, some velocity is that there is some angle between v1 and v2,
Ha,
like theta, then you have to consider the projection like v1 cos theta. Then in that case, if they are not in the same, let's say, direction or same line, then you have to
ha,
consider the angle in that scenario. So maybe you are
ha.
talking about that picture, so I'm not considering that picture here.
Yeah, not here, but since the topic is related, so I am asking this
Yeah, yeah, yeah.
question.
So yeah, you can, I mean, I think the best thing is to go through any textbook or any physics book. As a matter of fact, you can find it. I mean, these things mostly many people would have done this back in for JE or 12 standard, 10 standard maybe. So yeah, you can look it up in any textbook or anything. So I mean, we can
Oh,
discuss it for a very long time, but since we don't have the time, so I don't think we should invest more time on this.
yeah.
So you get the
Okay.
idea, right? So that's the thing.
Yeah, yeah, yeah.
I mean, depending on the situation, there can be other parameters as well. Velocity is a vector at the end of the day, of course. So in that case, if you I am assuming you are traveling, the source, the observer is traveling at a direction relative to the source at an angle of theta, then okay, I have to consider v cos theta. That's it. In this case,
Yeah,
since I am assuming that theta is 0, so cos theta is cos 0 is 1 because they are in the
yeah.
same line. So there is no angle, no phase
Huh.
difference. So that's the thing. All right.
And if
So
it is perpendicular, then cos 90 we will have to consider, na?
yeah.
Okay.
Now coming to your question, I think you are the one who raised this question of UV coordinate system. So there's a UV coordinate system. It's not exactly the Cartesian coordinate where you have like x and y axis which are 90 degrees apart. These u and v axes are actually 60 degrees apart, and 2 points are given, point A and point B, 1,2 and 5,4. What is the actual distance between these 2 points A and B if the side of each hexagon, remember we use hexagon cells, if the side of each regular hexagon is 1 kilometer, r is 1 kilometer. Okay, This is very important. Okay, please pay attention for this. Okay, so this was okay. We are in question number 12. Okay, so question number 12 is important. I mean, although it was discussed, but still I felt like maybe it would be helpful. First I will show you the straightaway formula. Okay, you can directly use this formula and find the distance in this case. So it is UV coordinate system. So first I will show you like the formula based approach. So there are 2 points. Point A, since we are talking about UV coordinate system, let me label them as U1 V1 as the first point, which is 1, 2. There is another point, point B, which is U2 V2, let's say is 5, 4 given. Now the distance let's say D between points A, which is U1, V1, and point is given by D equals to R root 3 square root of U1 minus U2 whole square, V1 minus V2 whole square, plus U1 minus U2 times V1 minus V2. So it has this analogy with respect to this. You know this D by R, the co-channel reuse ratio, right? That is square root of n, square root of 3n, right? And you know that n is the valid cluster size. It's of this I square plus j square plus ij form, right? And so in this scenario, basically you have this. If you choose I to be U1 minus U2 and j to be V1 minus V2, you get this basically. Okay, so this is the formula, this is the known formula. Yeah, good. Okay, so this is formula. So you can straightforwardly use this formula. See, and this is not the same as the typical distance formula between 2 points. Only the distance formula would involve this much only, square root of U1 minus U2 the whole square plus V1 minus V2 the whole square, but it's more than that. So for this problem here, R is given to be 1 kilometer, and you know U1 V1, U2 V2. So U1 is how much? 1, V1 is 2, U2 is 5, V2 is 4, correct? So substitute them, you get D equals to 1 times root 3 becomes basically 1, and this will become basically minus 4 square, which is 16, plus 4 plus this will be basically minus 4 times minus 2, which is plus 8. So this is, how much is it? So this is root 3 into root 28, so this is root 84, which is a 9.16, approximately 9.2 kilometers. Okay, because R is in kilometers, so of course overall unit is in kilometer. So now you go back to the options. So option B, option B, 9.2 kilometers. So this is how you calculate, but if you want to visualize it, actually let me try to give you a feel for that. So how this is happening, I mean, okay, so I mean visually I would say, so this is okay. How do I do this? Okay, so let's say this is your vertical axis, a V axis, which is also your Y axis basically, and this is my standard X axis. This is X axis, this is Y axis. These are perpendicular to it, we know that. Now this, if I align the Y and V as in the same line, now we have to keep in mind that is the angle between U axis and V axis is 60 degree, it's not 90 degree. So you can imagine a line like this, okay. So this will be your U axis, this angle is 60 degree and this angle is 30 degree, of course, okay. And if I assume these to be my origin 0, 0, then you need to know, okay, the first point A is 1, 2, point B is 5, 4. Okay, before I plot the points, I want you to recall, tell me what is the distance between the centers of two adjacent cells, hexagonal cells, assuming they are of radius r each. So let's say these are two adjacent cells, sides are r, this distance to vertex is also r from center. So what is this distance? Oops. What is this distance, the orange one? How much will be that? We have discussed these things before also. You have to be, so last time I showed you with a diagram like this equilateral triangle, right? So there will be basically these two will form two equilateral triangles. So, and we know the height of this first, each of these two equilateral triangles will be root 3 by 2 into 4, root 3 by 2 into r, because they are r. This is r, this is r, this is also r. So this height, overall height will be 2 times each of the height, which is root 3 by 2 into r, because height of an equilateral triangle of each side r, this height h is root 3 by 4, root 3 by 2 into r, right? So, and there are two such heights corresponding to the two equilateral triangles. So the distance connecting the centers of two adjacent cells is always root 3r. Okay, so that you have to remember. Now which color? Okay, let's say this. So for the first point A, 1, 2, what do? You will basically travel 1 unit. So see, 1, 2, so the u coordinate is 1, so you travel 1 unit along u axis and v coordinate is 2 and travel 2 units along the v axis like this, 1 and 2, and this will be your point A here. Okay, and each of this distance that you will travel is actually this root 3r. So this is root 3r. Okay, and so of course 2 units traveled along the v axis means 2 root 3r. Okay, and now in order to determine the coordinate of this point A, what I can do is, okay, its projection of this one along this will be root 3r cos 30. Okay, this distance, and this one will be root 3r sin 30. Okay, so the coordinate of A is basically this distance along the x axis, which is root 3r cos 30, comma this whole height from the x axis. So this is 2 root 3r plus root 3r sin 30. Okay, similarly you locate this point B. So in point B you travel 5 units, 5 is the u coordinate, 5 units along u axis. So already 1 unit we have covered here, 4 more units we have to do. So this is the third, fourth, fifth. So 5 units we have traveled. So basically this is 5 times root 3r. Root 3r is each unit. Okay, so of course if I project now for the v axis we have to go 4 units. So let's do that. This is 1, 2, 3, 4, somewhere here approximately. So this will give you point B, and this is 4 into root 3r. So again you just do this projection and all and just find the coordinate of this point. So this how much will be this height? Basically it's from the triangle root 5 root 3r sin 30, and this whole base would be 5 root 3 r cos 30 degree, correct? And you can now determine the coordinates of point B, which would be the entire that base length, which is 5 root 3 r cos 30 degree, comma the entire height, which is 4 root 3 r plus 5 root 3 r sin 30 degree, right? Now you have the two coordinates of the exact coordinates of the 2 points with respect to the x and y coordinate system. See, because I have projected on the x axis and y axis like that. So now you can simply find the distance between these 2 points using the known distance formula. So this is, let's say, DAB. Now you can do it, and if you actually simplify this cos and sine terms here, you will find that A comes out to be basically 3r by 2, because I mean cos 30 is root 3 by 2, so root 3 by 2 times root 3 gives you 3 by 2, so 3r by 2, 5 root 3r by 2, and b comes out to be 15r by 2 and 13 root 3r by 2. Just check it, and then this is just the normal distance. Usual distance formula in xy plane. Okay, so just do that. Basically, I mean x1 minus x2 the whole square plus y1 plus y2 y1 minus y2 the whole square, you will get something like, you know, this 4 root 3r whole square, which is some, and r is 1 kilometer given, so this is square root 84, which is again approximately 9.2 kilometers, and we found exactly the same answer here also. So this is visually, you can, you know, imagine, this is why we are not straightforwardly using the distance formula. So I mean, this is just the concept, it was already discussed, but still I wanted to discuss. So now 13 is there. Okay, 13 also, I mean, was a similar problem which was discussed by Professor David in one of the lectures, I think. Okay, so question number 13 gives you a table. Okay, table has two parameters. Distance is varied from 10 meters to 300 meters. We have 5 data points, and another parameter is the ratio of received power and transmitted power in dB. Okay, so 5 sets of data, and frequency is 900 megahertz. Path loss exponent is small m, that we need to find out, okay, such that it minimizes the mean squared error between the simplified model given below. So this is actual real data which is given in the table, experimental data, and the simplified model that is given here in this formula here is the approximate one. Now we have to find the path loss exponent that is used here, the small n, such that the difference, such that they are close to each other, the difference between the accurate data and the measured data is as minimum as possible. That minimizes the mean squared error between these two. So
Sir, this problem was, I think, taken yesterday, day before yesterday also, how to find this path loss exponent from these values.
okay. So
Just can you tell that actually that what is the formula is given here, that something minus 10 n multiplied by log 10 something d by d break.
yes.
Actually we know that that is should be d by d break to the power n actually.
Okay, I am coming to
why
that.
it is why it is negative n?
I am
Why
coming
it
to
is-
that. Okay, wait.
But you can clarify just only point. Actually, someone has said that was discussed in the earlier session. But you tell that why it should be minus n.
Okay, so let me go to that. Okay, so the form is a bit different, that's what I understand. So we are familiar, first of all tell me, this is the everyone can see that this is the breakpoint model, right? Because d break is given and this is the breakpoint model. In a slightly different manner it is given. So let me show you how this is actually obtained. So usually the form that we know is like this. This, right? So I mean received power at distance d equals to receive power at distance d break times d break by d whole to the power n. This is what we know. And now actually what we can do is this, I can write it like this: PR at d break is basically PT divided by 4 pi d break by lambda the whole square, and we have this. So I am replacing this by this. Receive power at distance d break, I am writing it as this: transmitted power by the path loss, like this. Now I can take ratio PR by PT. I bring this PT to the left side, so therefore I will get like this: the whole square times, okay, I can take the reciprocal of this second term. I can make it d by d break. For that I have to do, I think, minus n here. Okay, instead of n, if I take the reciprocal, it will become minus n. And now PR by PT, if I do in dB, basically taking 10 log base 10 on both sides, I get 10 log base 10 of this first term and this second term as well. So this minus n will now come as a multiplicative factor, since this is the exponent, so it will come as a multiplicative factor in front of log, and we have d by d break. And I think this is the form which is given here exactly. Yeah, so this is how it is approximately coming, but doesn't matter. I mean, it could have been a different model as well, but whatever model is given here, you have to use that and compare it with the actual measured experimental data, and such that it minimizes the the mean square error. So okay, some of you were saying that okay, it was covered in the other session, so should I work this out, like how to do this? Basically you need to find the loss function at the distance, basically mean squared error, and then differentiate it, because you have to minimize it, and for minimizing something you differentiate that to 0 and equate it to 0 and find that will give you the n, small n.
Most probably last session they have told that a derivative of Jn function actually.
Exactly. So
but that should be 0, and after that taking the derivative we can give the value of the n actually.
Yes. So I mean the process is known to you, right? So then I think I can maybe skip it actually. So you see, basically you have five points you need to consider. For one, you consider d equals to 10, the first point, which is this first point, d equals to 10 meters. Here you have this ratio PR by PT. Let me use a subscript 1 because it's the first point. Its actual experimental value in the table is minus 70 dB. Okay, this is minus 70 dB, and the value that you will have to calculate using this model, let me denote it by a cap like this. This is the one which is calculated using this formula. D break is given. D break is 1 meter. It is given. Okay. Go to the question. D break is 1 meter. It is given. And distance is known to you. Distance is 10 meters. So put d equals to 10 meters, and lambda you can calculate from that actually, given frequency. I think frequency was given in the question, 900 megahertz, right? So if your frequency is 900 megahertz, you can find lambda also. Lambda would be, I think, 1/3, I think so. 3 into 10 to the power 8 by 9 into 10 to the power 8, which is 1/3 of a meter. So lambda also you know. Only missing thing is this n. So just basically you put lambda 1/3 meter, d break equals to 1 meter, d equals to 10 meter, and you will get something like this, minus 20 log base 10 12 pi minus 10n, a function of n. N is the one unknown variable to you. So this is for one point, right? Similarly you do it for other distances. For d equals to the other 4 points. What were the 4 points? 20, 50, 100, 300. For d equals to 20 meters, 30 meters, 50 meters. What was the point exactly? 20, 50, 100 and 300. Okay, 20, 50, 100, 300 meters. So for the remaining 4 points you do it in the similar way. Okay, so you see, and then you find this is your basically an estimate of the mean square error, which will be like for the 5 points. So your PR by PT I, the experimental value, minus the calculated one, which I denoted by hat, summed over all the I. How many I will be there? From 1 to 5. I mean sum squared, because we talk about mean squared error. So this is error squared, right? So this is the thing. So this is your mean square error. Okay, this you calculate. This will be another like quadratic function of n. Okay, then differentiate it and with respect to n and equate it to 0. Why? Because we want to minimize it, and for minimization or maximization problem we always take the derivative and equate it to 0, right? So to find the value of n for which it is minimum. So that I think will give you something like 3.7 or something near about that. So you can check this. Okay, so that was your first part, finding the path loss exponent. And at the second part, basically you need to find the received power at 150 meter using the above model when the transmit power is 1 milliwatt. So that is simpler. Now you know n. So now you can simply use this formula of this model. You know lambda 1/3 meter, you know d break 1 meter, you know n, which is like 3.8 or something, 3.7, which I calculated, and just you need to find the received power. You know d as well, 150 meters. If PT is 1 milliwatt, you need to find PR. That's it. Okay, so that hopefully you should be able to solve. So basically this is the second part. PR by PT in dV is equals to 10 log base 10 all these factors, you know, all these lambda by 4 pi d break the whole square, if you put all the lambda equals to 1/3 meter and d break equals to 1 meter, you will get some 1 by 12 pi whole square minus 10 times n was there, right? So 10 into n, path loss, so path loss exponent, so that I claim that it is somewhat 3.7 or something like that. You should verify it. Log base 10 of d by d break was there, right? D by d break, yes, so which is 150 by 1 linear of this, and that comes out to be something like approximately minus 112 dB. Again, I mean, these values are not important, just you to be carefully calculating this. Now PT is 1 milliwatt given, which is nothing but your so 0 dBm, basically 0 dBm. Now therefore your received power would be just you know the ratio of them, so you have to basically add in the dB scale, so that is PT in your dBm plus this ratio of minus 112 dB, so that is comes out to be so this is all, this is 0 dBm because it's 1 milliwatt, so it stays the same, but dBm. So the received power would be at distance 150 meters would be minus 112 dBm. Now from dBm you can go to other units as well that you can do. dBW you can do, or you can simply express it in watts, milliwatts, like that also. So this, or if you want to stay to watts or milliwatts, then what you can do is this ratio, you know, this PR by PT ratio in dB that we got as minus 112 dB, and that becomes approximately some 6.24 into 10 to the power minus 12 in linear scale. Therefore your PR would be simply the product now. So this is and PT is 1 milliwatt, so 1 milliwatt is 10 to the power minus 3 watts, so this much watts, which is 6.24 into 10 to the power minus 15 watts, this is 6.24 femtowatts. So just, I mean, if you want to express in some other units also, you can do that, but yeah, that's the received power at distance 150 meters. So yeah, and just the last problem, I'll just run through it quickly. Actually, okay, so another cellular system is there. It has 84 cells, cluster size is capital N, 300 voice channels are there, and the users are uniformly distributed over the entire area. Each user generates 0.04 airlines of traffic. Okay, assuming block calls are cleared, and the blocking probability is 1%. Okay, now let's look at first part. We have to find the maximum number of users that can be supported in this scenario, and also the maximum carried traffic per cell when the cluster size is n equals to 4 and n equals to 12. I'll do for n equals to 4, you can do it for n equals to 12, it is the same process. So okay, so let me write the given information. Okay, so last problem, okay, I will just write it. 84 cells are there, 300 voice channels, okay. Traffic per user traffic, which we typically denote by a suffix u. Traffic per user is 0.04 erlangs. P blocking probability is 1%. Now case A I am considering for n equals to 4. So okay, these are the total number of channels, 300 voice channels, and there are 84 cells, and okay, and I am assuming cluster size of 4. Okay, so one cluster has 4 cells. Okay, so 4 cells in a cluster. Okay, 300 channels in cluster. Therefore, number of channels per cell in each of the cell would be basically 300 by 4, which is your 75. Now again, the link to that calculator has been given here. It's the same one which I already showed you. Go to that calculator using the Erlang B calculator. So for C equals to, let's say, 95, this is I mean number of channels per cell. Let me not use C here actually, for because C is already used for a different variable. For number of channels per cell equals to 75, which is that your lines parameter in the calculator, and P blocking equals to 0.01. Once you enter these two values, you will notice that the erlangs, the traffic A you will get as 60.7 erlangs. So this is your offered traffic per cell. We are talking about per cell. So basically this thing with okay, probability of blocking is 0.01, 75, right? 75. So if we do this, see 60.7 erlangs. That's what I just wrote here, and now that's the traffic per cell. Now let U be the number of users per cell in each cell. Okay, therefore traffic per user into number of users per cell will give me the offered traffic per cell. Traffic per user times number of users per cell will give me the traffic per cell. We already know the traffic per cell from the calculator, 60.7, and traffic per user was already given to us initially, this value 0.04 erlangs for each user. So this is 0.04 times U equals to 60.7, and that will give me U as 60.7 by 0.04, which is 1517.5. So that's the maximum it can go, right? So and u has to be a number, right, number of users, so it has to be an integer value. So 1517, the next lower highest integer we take basically. So 1517 users it can support in each cell. So this is u is number of users per cell. Okay, this is per cell. Therefore total number of users that can be supported equals to users per cell, which we just calculated, times number of cells, right? So users per cell is 1517 times how many cells are there? 84 cells. See, I wrote it before. Okay, this gives you 127428. That's the total users you can support. And for n equals to 12, same thing you have to do. So do it yourself, same process. Okay, and now let's go to part B. Okay, so part B says for the system in part A, same system, how much offered traffic, how much reduction in offered traffic will be observed in order to maintain the same grade of service. Same grade of service means the same as the probability of blocking. To maintain the same probability of blocking, that is 1%, what should be the reduction in offered traffic if one of the channel in each cell is reserved for handoff traffic. Okay, that channel is taken out, that is reserved for exclusively handoff traffic. So and we assume cluster size of 4, n equals to 4. So what will be the reduction in the traffic? So that's what is asked here. So one channel is reserved for handoff traffic. Okay, one channel in each cell, and same grade of service means same probability of blocking. Okay, now n is 4, therefore one channel in each cell is reserved for handoff. So how many channels in each cell are remaining? See, in the previous calculation we found that number of channels per cell is 75. Now out of 75, 1 is reserved, therefore we have 74 with us. So number of channels per cell in this scenario is 75 minus 1, because 1 is reserved for handoff, which is 74. And P blocking is the same, so P blocking is 1%, which is 0.01. And again you have the blocking probability, you have number of channels per cell 74. Again plug in that value in the calculator using calculator. So for the calculator, let me go back. So only by here you have to replace lines by 74 instead of 75. Calculate it. L lines comes out to be 59.8. So the new traffic you get is the offered traffic per cell is 59.8 L lines. So of course it got reduced, right? In the previous case it was 60.7, so now it is reduced. So therefore the reduction which is asked in the question, reduction in offered traffic per cell is equals to the new traffic, which is this minus the initial one. This is minus 0.9 lengths. So the drop is 0.9 lengths basically. All right, now this is so part B is also done, and going to part C. So these are based on just the tool, online tool only, or you can just use that. Now part C asks us to find the blocking probability using Erlang formula. So this time you don't actually need the online tool. This time you have to use the known formula. So offered traffic is given to you, capital A is given to you 1.5 Erlangs. Number of channels C is 4. Find P blocking. Okay, so P blocking. So the offered traffic per cell is 1.5 Erlangs, and number of channels is 4. Okay, we use A and C to denote them. Now use Erlang formula. This was again, revisit the lecture notes if you don't recall. So probability of blocking is given by A power C by C factorial divided by sum over k going from 0 to C, A power k by k factorial. Okay, and that turns out to be one in the numerator we have this by 4 factorial divided by this sum, it will be like this, and this, and if you just solve this you will get approximately 0.048 the answer. So that's the blocking probability using the formula. You don't need the tool for this part. So I think this completes all the questions. I took a longer than usual, so sorry for the delay, but yeah, I think that's all for today. I mean, we have covered the questions. So yeah, thanks a lot. So if you have any questions you can ask, or we can stop the recording. All right, so I'm assuming there is no questions, so we can stop the discussion. Yeah, is there any question?
No, sir, you can stop. Okay.
Okay. All right, okay. We will meet again on next Tuesday, and once again I wish all of you a happy Independence Day. All right, so
Same to you, sir, also.
yeah, thanks. Okay, you may sign off. Thanks.